In 1993, Amtrak introduced what appeared to be the future of American passenger rail. The GEP 40DC, first of the Genesis series, promised speeds up to 110 miles per hour, modern electronics, and fuel efficiency that would finally leave the 1970s behind. On paper, it was everything Amtrak needed, but within months of entering service, something unusual began happening. Engineers, experienced professionals who'd spent decades running locomotives, started expressing concerns about how the P40DC behaved at speed. They reported lateral oscillations, unexpected movements, and a ride quality that felt fundamentally different from anything they'd operated before. Some crews, when given a choice, began avoiding assignments on these units. This wasn't a case of outdated thinking or resistance to change. The engineers who raised these concerns were the same professionals who understood that their judgment was part of the safety system. And when that judgment told them something wasn't right, they spoke up. This is the story of what happened when locomotive design pushed past a boundary that hadn't been properly mapped, and what the industry learned from it. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The pressure behind the P40DC. By the early 1990s, Amtrak's locomotive fleet was showing its age in ways that went beyond simple wear and tear. The workhorse F40PH, introduced in 1976, had served reliably for nearly 2 decades, but its fundamental design created operational constraints that were becoming increasingly problematic. The F40PH's most significant limitation was its head-end power system. To generate electricity for passenger cars, the locomotive had to run its prime mover at high RPM regardless of train speed. This meant that even sitting at a station platform, an F40PH was running at near maximum engine speed, consuming fuel and generating noise. The continuous high RPM operation also accelerated engine wear and maintenance costs. For a railroad operating long-distance trains that spent considerable time idling at stations, this represented a substantial inefficiency. The noise issue extended beyond simple annoyance. In urban terminals like Chicago's Union Station, multiple F40PHs idling at full throttle created sound levels that affected both passengers and terminal workers. Cities along Amtrak's routes were increasingly vocal about diesel locomotive noise, particularly during nighttime hours when commuter and freight traffic was lighter, but intercity trains still needed head-end power. There was also the matter of speed capability. While the F40PH could reach 103 miles per hour, this was near its design limit. Amtrak's Northeast Corridor operations were looking toward higher speed service, and the existing fleet wasn't positioned to support those ambitions. The railroad needed locomotives that could comfortably sustain 110 miles per hour with room for future increases. Fuel costs presented another pressure point. The F40PH's constant high RPM operation meant poor fuel economy compared to what modern diesel-electric technology could achieve. With hundreds of locomotives in the fleet, even modest improvements in fuel consumption would translate to millions of dollars in annual savings. When Amtrak issued its specifications for a new locomotive generation, the requirements reflected these accumulated frustrations. The railroad wanted 110 to 125 mile per hour capability, separate head-end power generation that wouldn't force the prime mover to run at constant high speed, reduced weight for better acceleration and lower track wear, and modern microprocessor controls that could optimize performance in real time. GE's response would be more radical than Amtrak anticipated. Rather than evolving the traditional cab unit design, GE proposed something fundamentally different. A locomotive that drew inspiration from European high-speed trains and even aerospace engineering. The Genesis design featured a dramatically streamlined car body with an aircraft-like nose, a monocoque-style structure where the body shell contributed to structural strength, and an aggressive weight reduction program that trimmed thousands of pounds compared to conventional designs. This wasn't simply a cosmetic update. Every aspect of the design reflected a different philosophy about what a passenger locomotive should be. And with that philosophy came trade-offs that wouldn't become apparent until the units were running at speed on actual railroad infrastructure. Design departure. The P40DC represented a departure from American locomotive design conventions that had remained largely stable since the diesel era began. To understand why this mattered, you need to understand what those conventions were and why they existed. Traditional American diesel locomotives were built like bridges on wheels. Heavy frames, substantial structural members, and conservative weight distribution created machines that were fundamentally stable at the expense of efficiency. The car body was essentially dead weight sitting on top of the structural frame. It didn't contribute to strength, but it added mass that helped damp out oscillations and provided a stable platform regardless of what the trucks were doing underneath. The P40DC took a different approach. The streamlined car body wasn't just for aesthetics. It was a stressed skin design where the outer shell contributed to the locomotive's structural integrity. This allowed GE to reduce the weight of internal structural members, saving thousands of pounds. The narrow, tapered design reduced wind resistance and gave the locomotive a modern appearance that aligned with Amtrak's desire to project a contemporary image. But this weight reduction came with consequences that interacted with other design choices in ways that weren't fully anticipated. The lighter car body meant less mass damping out high-frequency vibrations and oscillations. The narrow body design, while aerodynamically efficient, concentrated weight over a smaller footprint, changing how forces distributed through the suspension system. The truck design reflected passenger service priorities rather than the freight-derived designs that had dominated American locomotives. GE optimized the trucks for smooth riding at high speed, using suspension parameters that prioritized passenger comfort over the absolute stability that freight locomotives required for heavy drawbar forces. The trucks featured softer suspension elements and different yaw damper characteristics than freight designs. Yaw dampers deserve particular attention because they became central to the P40DC's behavior. These hydraulic components control how much the truck can rotate relative to the car body as the train negotiates curves. Too stiff, and the locomotive fights the track geometry, creating harsh ride quality and accelerated wheel wear. Too soft, and the truck can develop unstable oscillations, particularly at high speed. The P40DC's yaw damper settings represented a compromise optimized for speed and ride quality. On perfectly maintained track, this worked as intended. But American railroad infrastructure in the 1990s was far from perfect, and the P40DC's suspension proved sensitive to track irregularities that conventional locomotives simply absorbed without issue. The elevated cab position, part of the streamlined design, also played a role. Engineers sat higher and further forward than in traditional cab units, which changed their perception of the locomotive's motion. Small lateral movements that would be barely noticeable in an F40PH's cab became more apparent in the P40DC's elevated position, where the engineer's eyes were further from the locomotive's effective pivot point. GE's design team wasn't being reckless. They were applying modern engineering principles and computer modeling to create a more efficient machine. But some aspects of locomotive behavior, particularly the interaction between suspension dynamics, car body mass, and track irregularities, were difficult to fully capture in simulation. The proof would come when these locomotives accumulated real service miles at sustained high speeds. The high-speed problem. The issues with the P40DC didn't reveal themselves immediately. Initial testing and low-speed operation showed a locomotive that performed as designed. The prime mover delivered rated horsepower, the head-end power system worked correctly, and the microprocessor controls managed the complex interactions between engine, generator, and traction motors without issue. But as the units entered regular service on the Northeast Corridor and began operating at sustained speeds above 90 miles per hour, crews began reporting something unexpected. The phenomenon they described was lateral oscillation, sometimes called hunting. At certain speeds, particularly above 90 miles per hour, the locomotive would develop a side-to-side motion that felt different from normal track-induced movement. This wasn't violent or dramatic. Observers standing trackside often couldn't see what engineers were feeling. But from inside the cab, the motion was unsettling. The technical explanation involves the complex interaction between wheel conicity, track gauge, and suspension dynamics. Railroad wheels aren't cylindrical. They're slightly conical, with the diameter larger near the flange than at the outer edge. This conicity, combined with the rigid axle connecting both wheels, creates a steering effect that helps wheel sets center themselves on the track. It's an elegant passive system that's been fundamental to railroad operation since the beginning. But this same conicity can create instability under certain conditions. As speed increases, the wheel set's tendency to oscillate laterally increases. Normally, the suspension system, particularly the yaw dampers, controls this oscillation, keeping it below the threshold where it becomes perceptible. The P40DC's lighter car body mass and specific yaw damper characteristics meant this threshold was reached at lower oscillation amplitudes than in conventional locomotives. The problem was speed dependent. which explained why it hadn't appeared in earlier testing. Below approximately 85 miles per hour, the P-40DC rode normally. Between 85 and 95 miles per hour, some engineers began noticing increased motion. Above 95 miles per hour, particularly on track sections with less than perfect geometry, the lateral motion became pronounced enough that it affected the engineer's ability to monitor instruments and maintain visual reference points ahead of the train. Track geometry played a crucial role. The Northeast Corridor's infrastructure varied considerably in condition. Some sections featured recently renewed track with precise alignment and proper superelevation. Other sections had subtle irregularities, slight gauge variations, minor alignment deviations, or uneven rail wear that stayed within maintenance tolerances but provided enough input to excite the P-40DC's suspension at its resonant frequency. What made this particularly troubling was the unpredictability. The same locomotive might run smoothly on one trip and develop noticeable oscillation on the return trip over the same track, depending on factors like wheel wear patterns, ambient temperature affecting yaw damper fluid viscosity, or even the weight distribution of the train behind the locomotive. This inconsistency meant engineers couldn't develop reliable mental models for when the motion would occur. The nose movement was another factor. The P-40DC's streamlined nose extending forward of the front truck acted as a lever that amplified any yaw rotation of the lead truck. Small angular movements at the truck translated into larger lateral movements at the engineer's position. This created a visual effect where the track ahead appeared to shift position laterally, not dramatically, but enough to be disconcerting when you're trying to watch for signals and track conditions at 100 miles per hour. The vibration characteristics also differed from what engineers were accustomed to. Traditional locomotives transmitted low-frequency vibrations, the solid rhythmic feel of a heavy machine moving over jointed rail. The P-40DC's lighter structure transmitted higher frequency vibrations that felt less substantial. Some engineers described it as the difference between riding in a truck versus riding in a car. Not necessarily worse, but fundamentally different in a way that affected their confidence in the machine. It's important to emphasize what this wasn't. There were no derailments or incidents attributable to P-40DC stability issues. The FRA's monitoring showed that the locomotives operated within acceptable safety parameters. Track force measurements confirmed that the P-40DC wasn't causing unusual wear or stress on the infrastructure. By every quantifiable metric, the locomotive was safe. But safety, in railroad operations, isn't purely about numbers. It's about the engineer's ability to maintain situational awareness and respond appropriately to changing conditions. When the platform you're standing on is moving in unexpected ways, it divides your attention between monitoring the locomotive's behavior and monitoring everything else. Track conditions, signals, speed restrictions, other traffic. That divided attention, even if only partial, represented a risk that experienced engineers recognized intuitively. Inside the cab, understanding why crews lost confidence in the P-40DC requires understanding what the job of operating a locomotive actually entails. An engineer isn't simply a throttle operator, they're a real-time data processor, synthesizing information from instruments, visual observations, radio communications, and the physical feel of the locomotive to make constant adjustments that keep the train on schedule while maintaining safety margins. The physical sensation of the locomotive is part of that information stream. Experienced engineers develop an intuitive sense for how a locomotive should feel at different speeds, under different loads, on different sections of track. They can detect wheel slip before it shows on instruments, sense when braking effort isn't distributing properly, and feel track irregularities that might indicate developing problems. This sensory feedback loop becomes automatic over years of operation. Engineers process it without conscious thought, freeing their attention for higher-level decisions. The P-40DC disrupted that feedback loop. The elevated cab position, approximately 8 feet higher than a traditional cab unit and positioned well forward of the locomotive's center, changed the relationship between locomotive motion and operator perception. Physics dictates that angular motion translates into larger linear displacement the further you are from the pivot point. Small yaw movements at the truck became noticeable lateral movements at the engineer's seat. The narrow car-body design amplified this effect psychologically. Sitting in a wide cab with substantial mass around you provides a feeling of stability even when the locomotive is moving. The P-40DC's cab, with its streamlined nose tapering away to nothing directly in front of you and minimal width at shoulder level, provided less of that psychological buffer. You felt more connected to the locomotive's movements because there was less visual and physical isolation from those movements. The forward visibility, ironically, contributed to the problem. The P-40DC's large windshield and elevated position provided excellent sightlines for signal observation and track monitoring. But this same visibility meant that when the nose moved laterally, the entire visual field shifted with it. Engineers described watching distant signals or bridge structures appear to move relative to the track centerline, an optical effect created by the nose's motion that made it difficult to maintain stable visual reference points. The instrument panel layout reflected modern design, with electronic displays replacing many traditional gauges. While this represented an improvement in information density and readability, it also meant that engineers had to shift their gaze more frequently between displays. When those displays were moving slightly due to cab motion, the cognitive load increased. Reading a vibrating display requires more concentration than reading a stable one, even if the vibration is modest. Fatigue became a reported issue, particularly on longer runs. Operating a locomotive requires sustained concentration, even under the best conditions. When you add the need to compensate for unexpected motion, unconsciously tensing muscles to maintain stability, continuously adjusting your visual focus, mentally filtering out motion cues that don't match your expectations, the cognitive load increases. Engineers finishing runs on P-40DCS reported feeling more tired than they did after equivalent runs on conventional power. The sound environment was different as well. The P-40DC's modern design and improved insulation reduced overall noise levels compared to older locomotives, which should have been an improvement. But the sounds that did come through were different in character. The higher frequency vibrations transmitted through the lighter structure created sounds that engineers weren't accustomed to, not necessarily louder, but unfamiliar. In an environment where anomalous sounds can indicate developing mechanical problems, unfamiliar sounds trigger attention even when they're harmless. Trust is fundamental to locomotive operation. Engineers need to trust that the machine will respond predictably to control inputs, that it will maintain stability under varying conditions, and that it will provide adequate warning of developing problems. This trust isn't blind faith. It's earned through experience and reinforced by consistent behavior. When a locomotive's behavior doesn't match established patterns, that trust erodes. The P-40DC didn't earn that trust. Its behavior was inconsistent enough that engineers couldn't develop reliable predictions. A trip that went smoothly one day might exhibit noticeable motion the next day under apparently identical conditions. This unpredictability was perhaps more concerning than consistent bad behavior would have been. At least consistent behavior can be anticipated and compensated for. Union representatives began receiving complaints from members. These weren't formal refusals to operate. Such refusals require specific safety justifications and trigger investigations. Instead, they were expressions of discomfort and requests for management to investigate the reported issues. Engineers who had seniority exercised their right to bid for assignments that avoided P-40DCS when possible. Junior engineers who lacked bidding rights requested union support in raising concerns with management. The phrase "refused to drive" overstates what actually occurred, but it captures the underlying sentiment. When experienced professionals with decades of safe operation start expressing serious concerns about a piece of equipment, it represents a breakdown in the relationship between operator and machine that extends beyond simple preference. It indicates that something fundamental about the design doesn't align with operational reality. Management response. Amtrak and GE faced a complex challenge. The P-40DCS were performing within design specifications and meeting all regulatory safety requirements. There was no documented evidence of unsafe operation. Yet the people who operated these locomotives daily were reporting concerns that couldn't be dismissed as mere resistance to change. The initial response focused on data collection. Amtrak installed additional instrumentation on several P-40DCs to measure car body accelerations, truck movements, and wheel rail forces under varying operating conditions. This data would either confirm that the locomotives were behaving abnormally or demonstrate that crew perceptions didn't match objective reality. The data revealed something subtle. The P-40DCS were experiencing lateral accelerations that, while within acceptable limits, were measurably higher than conventional locomotives under certain conditions. The accelerations were particularly pronounced in specific speed ranges and on track sections with particular geometric characteristics. The instrumentation validated what engineers were reporting. The motion was real, not imagined. Speed restrictions were quietly implemented on certain routes where track geometry and operating speeds combined to create the most pronounced effects. These restrictions weren't publicized as safety measures, but rather framed as operational adjustments during a break-in period. The practical effect was to keep P40 DCS below the speeds where lateral motion became most noticeable. Engineering investigations focused on the yaw damper settings. These hydraulic components had been optimized for ride quality based on computer modeling and limited testing, but the models hadn't fully captured the interaction between damper characteristics, car body mass, and real-world track irregularities. GE began experimenting with different damper fluid viscosities and piston configurations to increase the damping force without creating harshness in the ride. Maintenance procedures were revised to tighten tolerances on truck components that affected yaw behavior. Wear in bushings, pins, and bearing surfaces could allow increased play in the suspension system, which would amplify hunting tendency. By catching and correcting this wear earlier, maintenance teams could keep the trucks performing closer to AA's design specifications. Weight distribution also received attention. The P40DC's fuel tank was located toward the rear of the locomotive, meaning that as fuel was consumed during a run, the weight distribution shifted forward. This changed the loading on the trucks in ways that affected their dynamic behavior. Some operators began monitoring fuel levels more closely and adjusting operating speeds based on how much fuel remained. But the most significant changes were incorporated into the next generation of Genesis locomotives. The P42DC, which entered service starting in 1996, featured numerous subtle modifications to address the P40DC's characteristics. The car body was slightly wider and heavier, providing more mass damping. The truck suspension was retuned with modified yaw damper settings. The cab seating was positioned slightly lower and further back from the nose. These changes weren't advertised as corrections to problems. They were presented as ongoing design refinement. The P32AC-DM, a dual-mode variant developed for operations into New York Penn Station, incorporated even more substantial changes. This locomotive's additional weight from the third rail pickup equipment actually improved high-speed stability by increasing car body mass. The lessons from the P40DC were being quietly applied without public acknowledgement that there had been lessons to learn. GE and Amtrak had strong incentives to manage this situation carefully. Publicly acknowledging significant issues with a new locomotive fleet would have damaged confidence in Amtrak's modernization program and potentially exposed both organizations to liability concerns. If passengers became aware that engineers had expressed serious concerns about the locomotives, it could affect ridership even though the concerns were about comfort and confidence rather than objective safety. The strategy became one of incremental improvement without admission of fundamental problems. As P40DCS accumulated mileage and received routine overhauls, modifications were incorporated that addressed the reported issues. Trucks were rebuilt with updated components. Yaw dampers were replaced with revised designs. Weight was added in strategic locations. Over time, the fleet's behavior improved, though it never fully matched the solid, predictable feel of conventional locomotives. By the early 2000s, the P40DCS were being gradually displaced from the highest speed services by newer P42DCS. The older units were reassigned to routes with lower maximum speeds where their characteristics were less noticeable. This natural progression allowed Amtrak to reduce reliance on P40DCS without acknowledging that there were specific reasons for preferring other power. The P40DC fleet remained in service through the mid-2000s, eventually being retired as newer power became available, and as the units reached major overhaul points where continued investment became less economical than replacement. The retirement happened quietly, without retrospective analysis or public acknowledgement of what had made these locomotives controversial among the crews who operated them. The P40DC's legacy. The P40DC's tenure revealed something important about the limits of railroad engineering. Some aspects of locomotive design exist at the intersection of physics, human perception, and operational practice in ways that resist pure analytical solution. You can model suspension dynamics and calculate resonant frequencies, but predicting how those behaviors will affect operator confidence requires understanding factors that don't appear in engineering equations. The locomotive worked. It pulled trains reliably, met its design speed, generated the required horsepower, and operated for over a decade without significant mechanical failures. By conventional engineering metrics, it was a successful design. The issues that made it controversial weren't failures in the traditional sense. They were mismatches between design assumptions and operational reality. The most important lesson concerned the role of operator perception in equipment design. Engineers aren't simply throttle operators, they're active participants in the safety system, using their experience and judgment to detect and respond to abnormal conditions. When equipment behavior falls outside their established reference frame, it degrades their ability to perform that function effectively, even if objective measurements show the equipment is performing safely. The engineers who questioned the P40DC weren't refusing progress. They were providing feedback that the industry needed, even if it wasn't welcome at the time. Their willingness to speak up, despite pressure to accept new equipment without complaint, ultimately made passenger rail service safer and more reliable. That's the real legacy of the locomotive that engineers were uncomfortable driving.